This is Non-linearity and Shear-Dependent Viscosity for Polymer Rheology and Processing, Video 2. I discussed a series of mathematical models that apply to pseudoplastic or shear thinning behavior, which is the most typical nonlinear, non-Newtonian response when you're dealing with polymeric solutions or systems. Other common non-Newtonian behaviors in polymeric systems include Bingham fluid behavior and Thixotropy. In my particular research, I see pseudoplasticity, Bingham behavior, and Thixotropy on a regular basis, and they tend to go together. So to review, we talked about Bingham fluids a little bit, but to review, a Bingham fluid is a fluid that has a critical level of stress that must be attained in order to initiate flow. Below this critical stress, the material absorbs the stress energy without flowing. Once the threshold of this critical stress has been reached, the material yields to flow, and typically this flow is Newtonian in nature. This is the definition of yield stress. So that critical stress is also known as yield stress. Thixotropy is another type of non-Newtonian behavior that is time dependent. For some fluids, their viscosity does not reach a steady value for some time upon the application of stress. And so it takes time for the steady state to be reached, and that occurs when all the internal network structures are broken down by shearing, and then when the stress is removed, it requires time to rebuild that internal structure. So when you cease the shear rate, which causes the breakdown, the material reforms its internal network and viscosity recovers in what's known as a thixotropic loop. This is very characteristic. So here you have shear thinning in a typical pseudoplastic situation versus a Bingham plastic situation. So here you have something that behaves pseudoplastically in the solid line here, and here you have something that behaves like a Bingham fluid in this dashed line. So this shear stress here is also known as the yield stress. This has to be overcome before anything will flow. So once the shear stress reaches this threshold, you get flow that is more or less Newtonian after that. So again, the fluid depicted by the solid line does not exhibit a yield stress, whereas the dashed line does and behaves like a Bingham fluid. In a Bingham fluid, it will not flow until that yield stress is exceeded. The viscosity is infinite at zero shear rate, and that region is considered Newtonian. A Bingham equation describes shear rate and shear stress behavior of many shear thinning materials at low stresses, and it can curve fit the particular equations. The derived parameters depend on the shear rate range. Using this to predict viscosity can be somewhat unreliable. It is valid only under the following conditions, where n is small and the ratio of viscosity sub-zero to viscosity infinite is rather large. So this is the Bingham model. So first you start with a Cisco model, and if n in this situation is set equal to 0, we get this particular relationship. And you can redefine these parameters to be written this way, where this is shear stress, this is the yield stress, this is the viscosity, and this is the shear rate. And we've seen a similar equation like this in other lectures. And this is known as the Bingham Model equation. The Bingham extrapolation obtained from a laboratory viscometer has been used to predict the size of solid particles dependent on a gelled liquid. This model does not work in thickened aqueous solutions. The liquid slowly flows at stresses below the yield stress, and that's why it's not true Bingham behavior. The use of viscosity sub-zero and the Stokes drag law give a better prediction of the settling rate in this particular situation. If the settling rate is small and the suspension becomes non-settling or stable. So here we have a situation. This is a Bingham plot of synthetic latex over two different shear rate ranges. So here we have the shear stress versus shear rate, and you see a linear relationship here, and here you have the Bingham plot over a particular period of time and the yield stress shown here. This is the yield stress here in a linear relationship. This is the yield stress here. So again, this yield stress is reached and you get a linear relationship, and then you have a yield stress here where you get some amount of Newtonian behavior but not a lot. So this equation doesn't work for all situations, especially ones where you have particles that can settle like in a latex. There are effects of time in non-Newtonian liquids, and if we're going to talk about thixotropy, we certainly have to talk about those. So far, we've assumed that a given shear rate results in a corresponding shear stress that value does not change as long as the shear rate is maintained, and that is not always the case. The measured shear stress and the viscosity can increase or decrease with time of shearing, and these changes can be irreversible or reversible. So time is definitely a factor in non-Newtonian liquids. And the one that you tend to see in polymeric systems is thixotropy. The definition of thixotropy is a gradual decrease in viscosity under shear stress followed by a gradual recovery when the stress is removed. The perfect example of this is non-drip paint. Most paint these days is non-drip. You would definitely know if it was drippy paint and didn't exhibit thixotropic behavior. The shear thinning of this does not occur instantaneously. When you dip your brush in, you will spread the paint on the wall, and the paint spreads easily when the brush is applied to the wall, so you're shearing it that way. And when the brush is removed, the viscosity increases and the paint stays on the wall while it is drying and doesn't run down the wall in drips. The painter, or you if you're painting, does not really notice the increase in viscosity, but that's the reason why the paint doesn't drip down the wall once it's applied. It's that recovery period, which is actually very short, but is still a thixotropic recovery that keeps the paint on the wall without dripping. So what does this mean? This figure shows this relationship better. So a time-dependent decrease in viscosity, so here we have viscosity versus time. Shear is applied at this time, and under a constant shear rate or shear stress or shear rate, shear is applied. You have a thixotropic reduction in viscosity, and once the shear is removed, you get a gradual recovery in viscosity when the stress or shear is removed. So this can happen in a very short time span. So you spread the paint on the wall here, and the viscosity is low. You remove your brush, and it recovers so it doesn't drip off the wall. So this is what is actually happening. So you have a step change in shear rate over time. So you show this step change, shown here, and this is how the microstructure of the polymeric material behaves with that change. So here you have a breakdown of the internal structure of the polymeric system, and it reaches an equilibrium level of stress here, and when you remove the stress, it then rebuilds over time to another equilibrium level. This is also known as a thixotropic loop. When you're doing shear stress versus shear rate, you see this particular type of hysteresis loop. The viscosity of the thixotropic material does not follow the same path on structure breakdown as it does on recovery. When the shear rate is slowed, the stress path lags to form a hysteresis loop. So at this point, you kind of slow down the shear stress. So you start here, and you get kind of a yield stress, and it flows in pseudoplastically. And then when you remove the shear stress, it returns to a lower point than the critical initial shear stress. So it returns down to this point, much lower. And the area contained within this hysteresis loop represents the energy consumed in that structure breakdown. This is a very typical hysteresis loop for a thixotropic structure. I've seen numerous hysteresis loops that look like this from my own material. So, thus concludes video number 2 for nonlinearity and shear-dependent behavior. Thank you very much.